Hello, everybody. Thank you guys for coming. I hope you guys are having a great time at the conference. My name is Uttara Sridhar. I'm an engineer at the Amazon Elastic Container Service team. And I'm joined today with our customers, Manjiva and Thelina from McDonald's. And together we're going to talk about how to build your applications using Docker containers and how do you deploy them on Elastic Container Service. So let's get started. Here's the agenda of my talk. We're going to start by reviewing the software development lifecycle. And then we're going to see how containers are actually useful. And then we're going to look at the container ecosystem for each step of the software development lifecycle. By doing that, we'll see how to leverage Elastic Container Registry to store our images and Elastic Container Service to deploy our containers. We'll learn ways to automate monitoring and scaling and setting up CI/CD pipelines for fail-safe deployments. And then the team from McDonald's will give us a dive deep into how they built their home delivery system using Docker and ECS within 4 months to serve thousands of customers. Cool. So throughout the rest of my talk, I'm going to think about application and build that on containers. So of course, I come up with Hello World application, because once you're learning something new, everybody loves to see the words Hello World, because you know then it's working, right? So typically, in a software development lifecycle, we start with a developer writing some code in their local desktop. And then they push their code into a version control repository. And then from then on, a build is triggered, and artifacts are constructed. And these artifacts are then pushed into a repository. And then they're staged into a testing environment where some tests are run against the new artifact that's been built. And once we know that all the tests succeed, this artifact is now ready to be deployed to our production environment. So we also want to automate our way to actually go from a local desktop all the way into production without explicit approvals along the way. And this mechanism is called continuous delivery. Now, continuous delivery enables us to reduce risk and deliver value faster by providing us some reliable software and short iterations. And this is where containers fit in right well. Let me back up a little bit. I believe most of you here already know what containers are and the benefits that container bring to you. But I'm going to give a quick recap to sort of level set the rest of the discussion. So containers are similar to hardware virtualization, but instead of partitioning on the machine, they actually isolate the processes running on a single operating system. Great. So why are containers useful? Because they provide us with a reproducible and consistent environment throughout the software lifecycle. So there's very few chances for introducing errors along the way. And they're super lightweight. That helps us to increase our speed and agility in our delivery process. Great, we're all sold. We want to use containers. But how do you get started, right? Let's go back to our software development lifecycle. Our first step is source code. So we want to containerize your source code. And we start by doing that using Docker files. Now, Docker files are a simple text file with a syntax that allows you to define the environment your application is going to run at and all the dependencies that it comes with. So in this example, we're building a Hello World application. We start with a simple base image, which is Ubuntu 12.04. Then we use the run instruction to actually update your package cache. And then we use the run instruction again to install Apache. After that, we're just going to write Hello World into the documents root. And then we use the expose instruction to expose port 80. And then the command instruction to actually run your application. So you sort of get a picture of how to construct a Docker file. All right, here are some best practices and some caveats you need to think about when you're constructing a Docker file. You need to analyze all the dependencies that you bring in and just bring in what you need, like reduce everything else that you don't want. And make sure that you avoid using latest or stable tags for images, because the purpose of containers is for it to be consistent and reproducible. So we want to use specific versions so that it helps us roll out the software and roll back whenever needed. Great. We made some changes to our source code. We've pushed this to our version control. What's our next step? It's to build. So when you build an application with a Docker file in it, it results in something called a Docker image. So a Docker image is a lightweight executable package that includes everything that you need to run your application. It includes your source code. It includes your dependencies. It includes your environment variables and config files, whatever you need to actually run your application. And that makes it very self-contained so that you can make your deployments and scaling much easier. Great. Another advantage is it's consistent and it's immutable. So no matter when you run it or where you run it, it behaves the same. OK, this also helps us with our application portability needs. Perfect. So how do you get to the Docker image again? You just simply run docker build locally. Or you could use the Jenkins plugin called CloudBees build and publish plugin that lets you sort of specify the image that you want, tag it. In this case, we're tagging it with the build number. Then you specify the registry where you want to actually push your image so that it goes and gets stored there. In this case, we're using the AWS container registry. OK, what is that? Amazon Elastic Container Registry is a Docker containers registry that is fully managed, and it stores and manages Docker containers. Cool. It is also, it hosts your images in a highly available and scalable manner. It uses S3 under the hood. And then it has tighter integration with Amazon IAM. So you can do some resource level permissions, like give push permissions to some accounts, whereas pull permissions are open to everybody. It's up to you how you want to configure it. Great. So basically, ECR, Amazon Elastic Container Registry, eliminates the need for you to manage your infrastructure hosting these Docker registries. And it has tight integration with Amazon Container Service, and we're going to use that to actually deploy our containers. Cool. And this is how you would set up. You start with AWS CLI or APIs for ECR, and then you would create a repository. Once you have a repository, you'll get a registry URI, and you will use that after you build your Docker image. You go tag that with the URI. Cool. And then you do a Docker login to authenticate yourself. And then you're able to just run Docker push and push your image. And remember, this is under the hood what happens. You can do this manually, or you can just use the Jenkins plugin, and you don't have to worry about any of this. OK, moving on. We have our build that's complete. We have our image that's pushed to a registry. Our next step is to actually run tests. You can run some tests inside of a container. You can run them against a container outside. You can run unit tests, integration tests, black box tests, whatever makes you actually validate and confirm that the built image is actually now ready to go to production. OK, so we're ready. And how do we deploy now? So this is where Amazon Elastic Container Service comes into picture. Amazon Elastic Container Service is a highly scalable container management and orchestration service. It scales seamlessly for any cluster of any size. So whether it be tens of containers or thousands of containers, it's going to give you the same consistent performance. OK? It also has a set of APIs, set of schedulers that it offers that performs different placement strategies and helps you place your containers on the instances. So some examples include a spread. So you can spread your containers across different availability zones that probably caters to your availability needs. Or you could package all of these together in one instance and bin pack them together that caters to your cost efficiency. So you can have multiple placement strategies to place your containers, and McDonald's has leveraged that placement strategies that we'll learn later to build their system. Cool. Amazon ECS is deeply integrated with a lot of AWS services. This includes CloudWatch for logging and monitoring. We'll see that in a while. And then it also is integrated with application load balancing for you to front your service with a load balancer and route traffic to it. You can also, and it's also integrated with application auto-scaling. So in case of peak load, you can actually scale up and down your service. Another advantage that's listed up here is extensibility. The reason we say that is we offer a set of APIs that exposes the state of the cluster, like the number of resources that's behind the scenes. So customers can consume that and actually build their own custom schedulers on top of us. Cool. So let's do a quick recap of all the core concepts that ECS offers. So there is a concept of cluster. A cluster is basically a logical grouping of all the resources that you have. Next is container instances. Container instances are EC2 instances with our ECS agent installed on them. And ECS agent is a piece of software that's open sourced that sort of looks at the state of the world on the instance and sort of reports back to our backend service. Then we have something called a task definition, which is actually how you define your application. A task is actually an instantiation of that task definition. And lastly, a service runs and maintains a desired number of copies of the task above. Cool. So let's get back to our Hello World application. So far, we've written a Docker file. We'd push that image to ECR. Our next step is to create a task definition. And over here, we start with a Hello World task definition. We're using the image that is the ECR image. Then we specify the CPU and memory that's needed for that, the port mappings, because we have exposed port 80. And pretty much that's it. And then you're ready to go to actually start a service from there. But to take advantage of other things that task definition offers, you can group multiple containers together in a task definition. You can attach and mount volumes to the task definition. And you can also link the two containers together and establish a network for them to talk to each other. So there's a bunch of capabilities that you can leverage by defining what you need in the task definition. OK. We have our task definition. All we need to do is now actually run it. So what we do is we create a service, because it's a web app. We want it to be running continuously. And I've just put up saying that I need 10 copies of that. OK? Now, when these 10 copies come up, you want them to be able to be discovered easily. So for that, what we do is front it with a load balancer. Whoops. Go back. Front it with a load balancer. What that does is, as soon as a container comes up in the background, our ECS scheduler is going to just register these containers to the load balancer. That makes the discoverability easy. The other thing that it does is, if a container were to die accidentally, then our ECS scheduler will be able to recover those containers. So ECS service is super useful for such long-running applications. All right, there are some other things that you need to think about when you're actually running a service in production. Some of the key things are like deployment, logging, monitoring, and scaling. So let's start with deployment. ECS provides you some knobs to actually specify the deployment batch size. So you can specify that with two parameters. One is by specifying the minimum healthy percentage, which defines the minimum number of containers that you always want up and running in your service during the deployment. The other parameter that you specify is the maximum percentage, which is the maximum amount of containers that you have to run during a deployment. So let's elaborate a little bit on this. So let's look at an example. So you have a service with all green images, running 4 copies on 5 instances. So you have 4 tasks up there. They're all green. And now you have deployed a new purple image that you want to roll out to your service. So what you do here, you've specified the minimum healthy percentage as 50. And by doing that, what the service scheduler, the native service scheduler that ECS has, it will take down 50% of your green tasks and replace with new purple tasks. So that's what you see in step 2. So 50% of that is taken down and replaced, and now purple tasks are up and healthy. And in step 3, it will take down the other green ones and replace with the purple ones. Another example is to look at when the minimum healthy percentage was 100%. What happens at that point? All the green ones are kept as it is, and new purple ones are launched. That's what you see in step 2. And when the green ones are complete, when the purple ones come up, the green ones are turned down, and then your service is stable again. But if you observe the difference between the last slide and this one, let me go back. And this one, you'll see that because we had specified minimum healthy as 100%, we needed new instances to satisfy the need for our purple tasks. So this required a scale up of the instances in your cluster as well. Cool. We have deployed our service now. Our next thing is to get some logs. So AWS has a service called Amazon CloudWatch, which is a logging, monitoring, dashboarding, and alarming system. So ECS has native integration with CloudWatch. We also have other log drivers like syslog and journald that we use. And with respect to CloudWatch, you can specify different parameters like the log group and the log stream prefix that lets you sort of discover these logs easily for your containers. So this is how you would specify that. In a task definition, again, you go back, you edit the task definition to include a log configuration, and then you set the log driver as AWS logs, and you can take the options as the log group, the region that you want it to be published to, and a stream prefix. Cool. OK, we're ready to troubleshoot if something goes wrong. We have logs. But wait a minute, how do we know when something goes wrong? We need to be able to monitor it. And ECS provides some default metrics like CPU and memory utilization and reservation for you to measure how your applications are doing. So these are some default metrics that ECS provides. But additionally, you could also look at your error metrics in your logs. You could look at your search queue length metrics on your load balancers. You can look at whatever metrics that you want to monitor the health of your application. Let me show you how it looks at the ECS console. This is an illustration of how we show the memory utilization and CPU utilization. To circle back, memory utilization is actually the percentage of resources that's currently being used, and memory reservation is a metric that tells you how much is currently allocated in your cluster. Cool. So you have metrics publishing now. Our next step is to automate actions if these metrics breaches thresholds, because you don't want to do this manually, right? And ECS has deep integration with application autoscaling that lets you scale up your ECS resources. This could include your ECS services and the containers running in it. And additionally, it could include the EC2 instances that you need to get your applications running. So the way you do that is by looking at, by creating an alarm for your service, and you specify the threshold that you want, beyond which you want to configure some auto-scaling policies, and say that you want to increase your desired count for a service by 10% if it breaches your threshold by 50%. And you can configure such rules. So this is for ECS service, and this is for ECS cluster. So very similar configuration. Other best practices and metrics that people look at are if you're running a service behind a load balancer, you want to look at search queue metrics that tell you how much load you have, and if there's a peak, then you probably want to scale up your resources to handle that load. And if you were running a batch type workload, so if you have an SQS integration, then you can also look at approximate number of messages visible and sort of scale up your cluster accordingly. All right, so we've looked at different pieces and dove deep into what we have to think about at each of these steps. Our last step now is to tie everything together and try to automate as much as possible. So we do that with creating CI/CD pipelines. There are multiple ways for us to do this. So you could use AWS code pipelines with Lambdas to achieve that. Or you could use some of the solutions that our partners provide using Jenkins and Shippable. One such example is using Jenkins. So you start with your version control. It could be a AWS code commit, or it could be GitHub, wherever you want to start. Then you push your code there, and that push triggers a Jenkins build. And it uses the Jenkins plugin to build the image and push that image into the ECR repository. And then once that's done, it goes in update service on ECS. And what ECS does is goes and pulls the latest image and then rolls out that to the service. Awesome. So this is our summary of the individual steps and different options that you guys have to actually leverage and try to move your containers, move your application to containers, and how you would leverage ECS to actually deploy them. I'm going to now hand it over to McDonald's to learn about how they built their system. So here you go, Talina.
Perfect.
Yeah.
All right. Thank you, Uttara, for that great session on developing with ECS as well as taking ECS workloads to production, right? Good afternoon, everybody. Hope you guys are enjoying reInvent. My name is Talina Gunasinghe. I work for McDonald's Corporation. So we're here to talk about how we at McDonald's use ECS to massively scale our home delivery platform, right? Let's get right to it. So we'll talk a bit about McDonald's and our home delivery solution, but most of the time today will be spent on really how we achieve these things like scalability, speed to market, security, DevOps, and monitoring. So here's some interesting facts about McDonald's. We have 37,000 restaurants spread across 120 countries globally. And we proudly serve about 64 million customers every day, right? As you know, scalability is a difficult problem, but scalability with a distributed network like this, as well as this level of volumes in terms of scale, is even a tougher problem for us to solve, right? We'll talk a bit about that as we go on. Here's some of the velocity accelerators that we at McDonald's use. Number one being our digital transformation. The whole premise of our digital transformation is to make it more convenient as well as personalized for our customers, to make the whole experience personalized. The second pillar is delivery, again drawing on that convenience theme. How would we deliver our food to you when you want to have our food, right? And then the third aspect is the experience of the future. This is to actually elevate the restaurant experience and modernize the restaurant experience for our customers, right? So let's get to the home delivery solution. This is where we used ECS to really scale. We think of this as you as a customer going to something like Uber Eats and ordering McDonald's food for delivery, right? So that's kind of the business problem and use case. As we work with multiple delivery partners in the world, here in the States we use Uber Eats, and in European countries we have other partners. Asia countries we have furthermore partners, right? We've used a generic experience flow for you to walk through the user experience. It starts by basically you picking up a restaurant to order from. Then you obviously browse through the menu, right? And I've used our signature crafted sandwiches here to illustrate. And then you basically complete your order, build your order basket and complete your order, right? At this point, the order is complete, and then when the delivery rider or driver is close to one of our restaurants, the order gets released to the restaurant, because we believe in making our food fresh as much as possible, as well as giving it to the driver to be delivered to you. So that's kind of the whole business problem that we're going to talk about. So what were some of the critical business requirements for this, right? So Uttara mentioned about speed to market, right? So this was actually a 4-month duration for us, and that's from going from a idea to a concept to development to massive scale, right? And that's kind of the new norm that we see every day, right? Scalability and reliability, 250 to 500,000 transactions, and the notion of peak hour for us happens 3 times a day, every day, right? Because you got to eat, there's breakfast, lunch, and dinner, right? And to put this in perspective, this 250 to 500,000 transactions per hour translates to about 20,000 transactions per second, right? So that's kind of the scale that we're talking about here. Multiple country support, as I said, there's different countries have different business requirements, business rules, and then also different delivery partners such as Uber Eats, right, to work with. So the platform had to do that. And then finally, the cost sensitivity, right? So again, we're not talking about selling big screen TVs here. You're talking about an average check size of about $3 to $5, as low as that, right? So cost sensitivity is a pretty big thing for us as well. So we're going to spend a bit of time on our architecture. So this is a under-the-covers look of our architecture. Let me see here. So the experience that we went through starts here, which is the third-party delivery platform, right? So think of this like Uber Eats, right? Then all our APIs are hosted through what's called an API middleware, right? This is consistently using the API gateway pattern, right? These are all REST APIs. That's then wired through ALBs to ECS, right? And as you can see, ECS is the heart of the solution. Within ECS, we have multiple microservices. For illustration purposes, we've used 2, right? But it's important to understand that these microservices also have different scale and runtime profiles, right? So for example, some services that are customer-facing will have tremendous scale, tremendous reliability, tremendous performance requirements, right? Because it's front-facing, you're hitting that 20,000 TPS all day long, right? Some services could be more like about complex event processing type scenarios where workload optimization is what's important. As Uttara mentioned, you could use different scale profiles using the auto-scale policies and CloudWatch alarms to trigger the auto-scale policy, as well as you could use things like task placement strategy to further optimize, right? And we will go into a bit more detail about how we did that to achieve that scale. Obviously, the order goes to the restaurant, right? And then behind the scenes, for eventing, we use SQS, right? So think of this as one service wanting to talk to the next service, right? Through an asynchronous pattern, we use eventing exclusively for that, right? And it's not just about scale, it's also to be highly responsive and performant, right? To do that, you need to have a lot of things in memory, right? So we use Redis as our distributed caching platform, right? And it's actually hosted through Elasticache, right? So that's how we really hit those transaction volumes at about 100 milliseconds or lower, right, for each call. And then obviously, it cannot only be on memory, so you have RDS backing Redis up, as well as S3 for some of the more unstructured data. All right, so that hopefully gives you an idea about our architecture and how we achieved some of these big volumes, such as 20,000 TPS. So what were some of the principles that we use, right? Again, microservices this is not going to be a talk about microservices, but here's some principles that we use, right? Having your clean APIs, right, was number 1. Then having a good service model behind that API was number 2, right? And then it depends on what level of isolation you require, right? So your data model to be isolated, as well as your deployments to be isolated so that each microservice can be deployed independently, right? So getting your microservice strategy is critical for containerization, right? And then once you get the containerization right, orchestration of that containerization is very important to massively scale, right? And this is where a platform like ECS shines, because you get most of them out of the box. We also made a conscious decision to use most of our platform services from AWS. This is rather than you maintaining your own database cluster or you maintaining your own caching cluster, right? Use these services because they're scalable out of the box, right? So that was a conscious decision that we made. And finally, for the developers and software engineers in the room, right, your programming model, right? If you are, again, having a highly critical customer-facing microservice, use a synchronous programming model, right? If you are having a complex event processing type scenario, use an async programming model. Use that programming model to build your microservice and then containerize, right? That will save you a lot of time. All right, so let's go under the covers and really hit some of these things, right? So we're going to talk about speed to market, right? How we achieve that, scalability and reliability, what type of task placement strategies or auto-scaling policies did we use, right? We're going to get into the meat of that. Security is all about, reducing your blast radius and attack vectors, right? So how did we do that at the container level as well as at the service level, right? Finally, we'll talk about DevOps. How did we integrate our DevOps pipeline, which was based out of Jenkins, and then also monitoring. Once you take it to production, how do you monitor significantly? So let's get right to speed to market, right? We talked about the 4 months. It's not just about the 4 months though, right? It's about also showing progress back to your business, right? In this case, how do we build this continuously and show progress? And we had like 2-week dev iterations for this, right? Where ECS and containers really help is you could really have your dev containers, then go to staging, show progress to your business users very rapidly, right? So that was one of the big premises of this, right? Then the second thing is the polyglot tech stack, right? So you're bound to have code that's written in different languages, right? So in our case, we have some code in .NET and some code in Java, right? Some of this might be legacy code that you need to port over, right? Some of this might be like Java's better than .NET for certain things, right? But in the good old days, you have to like do native integration from .NET to Java, right? But the beauty of something like containerization as well as ECS is now you could host it in 2 different containers, right? And make the 2 containers talk to each other through an API, right? So that was also a pretty big benefit to achieve speed. The simplified ECS deployment model, Uthra went through that in detail, so I'll skip that point. Here's another important thing, right? So typically you, as good developers, we all write code, right? And then we basically do a level of testing, do a level of performance testing, right? And then take this massive cycle of integration and scaling, right? So to hit these volumes, normally it takes a long time, right? But the good news is if you containerize this right and use ECS and the correct auto-scaling and task placement strategies, we almost got this out of the box, right? So this was a pretty significant point for us. And then finally, the DevOps integration, ECS integrating with our DevOps toolchain very easily really helped us, right? So that's speed to market. Next, we'll talk about scalability and reliability. So I'm going to introduce one of my solutions architect, Manjeeva Silva. He's going to talk about not only scalability and reliability, but also security and also DevOps, as well as he'll end with some real-world container problems that we had to face and overcome, right, to scale to this level. Manjeev?
Thank you. So, I'm Manjeev Silva. Let me, for the next few slides, what I'm going to do is I'm going to run through how we use ECS as well as other AWS features to achieve the non-functional requirements, right? So let's start with scalability and reliability. So as Tilna mentioned, we got the scale targets to achieve 250 to 500,000 orders per hour with about 100 millisecond response time. So how we achieve this? By using auto-scaling, which ECS provides out of the box, right? As Uthra mentioned, right? You just have to configure the policies for the auto-scaling, and it will work. So ECS auto-scale will provide 2 levels of auto-scale. One is for the ECS, the EC2 layer, which will scale your EC2s. And the second layer is to scale your tasks. So how we approached this was we initially did some performance test to run some load to mimic our production to identify what is our production load is going to look like. Because this is really important. You need to know how is your load is going to look like in the production. So with that, we were able to derive the attributes or the thresholds for those auto-scaling policies. So then we configure the EC2 auto-scaling policies as well as the container auto-scaling policies. And also, it's very critical to get these values corrected, because otherwise you will have some issues when you are scaling out as well as scaling in. So it's pretty important to get that corrected at the first time. So once we're done with that, we were able to achieve the targets, right, to 250 to 500,000 orders per hour. And the next task was to kind of fine-tune this more, right? So we got 2 more requirements, as Tilna mentioned before. The 2 requirements that we got was to make sure some of the containers should run in isolation, right? So we had some requirements say that, for instance, certain country, we need to run those containers in isolation from the others, right? So that was one of the requirements. The second requirement was the cost sensitivity, means that you need to optimize your cost, right? So those 2 requirements we were able to achieve by using the task placement strategies and the constraints. So I just want to show how we use the task placement strategies and the constraints. I have given like 3 examples here, right? 3 services. And these 3 services will have different requirements in terms of scalability and reliability, right? So let's take the first service. So the first service will require a high availability and also reliability. And the second service, we would like to, it's just a batch mode, batch processing mode, but that requires we need to optimize the load on the cluster. So that's the requirement for the second service. The third service, which I was talking earlier, which requires some kind of isolation from the other containers. So let's go back and see how we use these placement strategies and constraints to achieve this, right? So I just want to put to this diagram. So the diagram shows you, right, on the top you can see the tasks or the containers get auto-scale using the policies that you have configured, right? And the bottom you can see the EC2s are getting auto-scale, again, using the auto-scaling policies that you have. And in the middle, you can see the task placement strategies and the constraints are applied so that the ECS can decide exactly where the task has to be placed, into which EC2 has to be placed, right? Okay, let's go back to those 3 examples that I had. First, service 1. Service 1, if you can remember, it requires high availability, which means that we need to have that task across all our availabilities, right, zones. So for that, we use the placement strategy called spread, and the attribute here we have specified as availability zone, which means that when the ECS plays in those tasks, it will make sure that it will place all the tasks across all the availability zones that we have in our cluster, right? But as Sutra mentioned, you can have different attributes, like you can have instance type or instance IDs, depends on your use case. But for us, it's the availability zone. Okay, let's go to the service 2. Service 2 was a batch processing service. So we want to make sure that process runs in a more efficient way, right? So that will kind of goes to our cost optimization. So for that, what we selected was to bin pack on the memory. So with that, ECS will make sure that all this, when they place in the new containers or the new tasks, it will make sure that it will optimize the memory on the cluster, right? And then we get a cost benefit out of it. The task 3. So task 3 requires some kind of isolation. So for that, what we do is we create a task group, right? And then when you are placing these containers, we say that, okay, place these containers with this task group. So also when we configure the other rules, we can say not to place these other containers if there's a container that is tagged with this particular task group, right? Okay, so let's move to security. So this, again, a big thing on these days, right? Security, especially when you're running containers on a cluster. So just want to touch up 2 things. One is the container security, and another one is the ECS instance security. ECS instance is basically the EC2, the host security, right? That's a term that AWS has. So let's go to the container security. This container security we control by using IAM policies. We'll make sure that we give only the permission that is required for the others, for that container. So you can control all your AWS resource access through the IAM policies. So you don't want to give, like, for instance, if the container does not require any elastic cache access, you don't want to specify that, right, in your policy. Just specify what is just the minimum security you need, access you need onto the container. The second point is kind of inherited from our architecture. As Tilna mentioned, a lot of the inter-service communication is happening through the eventing pattern. Because of that, we don't have a lot of API exposed to between the services. That will reduce our attack footprint. The second point is ACS instance security. So this is important because all these containers will run on these EC2s, right? You have to make sure these EC2s are patched and hardened so that there's any vulnerabilities on the cluster. So for this, we use we have an automated process that we get the latest AWS ECS optimized AMI, and then we apply our own hardening and we install our own security clients on that, and then it will spit out the application-specific AMI. So we call this process as our AMI factory. It's automated, and also AWS has a SNS topic. Whenever they publish a new AMI, they will publish a notification to that SNS topic. So we kind of subscribe to the topic. Automatically, the pipeline will run that, and we'll get the latest AMI. And that gets hooked into our DevOps pipeline. So that's what I'm going to talk about next. So DevOps and CI/CD. So this was really critical for us since we have to deliver this within a very short time, right? So we need to get this from the day one. We cannot do DevOps at the end of the development, right? So it has to start with the development when we start this. So the base of our DevOps pipeline is having two components, main components. One is the Jenkins, the one is the Terraform. So Jenkins basically does the orchestration of the pipeline, right? Getting everything compiled and download. And the Terraform will take care of the deployment of the containers to the cluster as well as the other AWS resources. So just want to walk you through with the pipeline very high level. So you start with, as Uttra mentioned, right? You compile the Docker image, and we have some validation script which will validate the integrity of these images to whether they are using the correct base Docker image and all our configuration is correct. And once that's done, it gets uploaded into a S3 bucket. And then from there, the Jenkins pipeline will get triggered. And the Jenkins will get the Docker images. Again, it will run some integrations test to make sure all the integration tests are passed. And if that is good, it gets uploaded to the ECR, which is the repository for the images. And from there onwards, the Terraform will take over, download those images, and then it gets deployed into the cluster. Right. Okay. So next is monitoring. So we use two components for monitoring of the platform. The first one is New Relic. The second is the Elk Stack, right? So New Relic we use to get all the telemetry data of the EC2 instances, containers, as well as the AWS PaaS components, like the SQS, Elasticache, and all that. So we get all that telemetry data into a dashboard. So we can see, in one dashboard, everything about the EC2s, the containers, as well as some of the AWS PaaS components. So for the application login, we use Elk Stack, right? That's a typical the Elk's implementation. But for the log driver, which Uttra mentioned, right? ECS supports many of the log drivers. Here we are using syslog, which it will stream all the logs of the containers to Logstash, and the Logstash will forward that to the Elasticsearch. And the Kibana we use for the visualization. Since we are not, in our containers, we don't store, there's no persistent layer, right? So we don't persist anything on the containers or the EC2s. So everything gets streamed out to Logstash. Okay, so finally, I just want to touch up 2 points that these are the challenges that, few of the challenges we had, right, during our this 4-month development. The first one was, it was due to, we were getting out of memory errors of the containers. So this was a known issue between even the Docker and the Linux community. The issue here is the application runtime which runs inside the container, it's not seeing is the container memory limits. So it will see the host memory limits because of that the garbage collection is not triggering properly, and the result is a out of memory exception. The root cause for this is the C groups are not, I would say, container friendly or containerized. Because of that, the application runtime will not see those memory limits, right? There are few workarounds to go over this. The one is that if it is Java runtime, you can set the heap size to a certain limit. Unfortunately, at this time, we were running a .NET Core. That version did not have that feature. But I think the latest .NET Core version have the same feature as the Java heap size. But at that time, we decided to use this LSCFS file system, which will kind of virtualize all the C groups into the runtime. So the runtime can now see the memory limits which the container has. The second is related to network. So by default, ECS provide different actually now it's 3. But initially it was 2 network modes. One is the bridge, another one is the direct network connection. So as a default, we are using the bridge network, which means that all the containers are placed behind a Docker bridge. So the Docker bridge gets connected to the host Elastic interface, network interface. But we had a different requirement from our security group to route all our container traffic through a different Elastic, like a secondary interface that we have in our host. But the issue here was the Docker bridge was not honoring that routing rule. It was always hardwired to the primary interface of the EC2. So because of that, we were not able to make use of that feature. So what we did was we have to do some custom implementation on the Docker bridge to make sure that all the traffic that gets routed to the secondary interface. So that was a custom implementation that we did at that time. But I think now, a few weeks ago, ECS team have released exactly the solution that we wanted. Right, it's called the AWS VPC, which will allow you to directly bind your Elastic interface to a Docker container or a task. So now you can have one-to-one IP mapping for your task to your network interface, which will give you a lot of capability of, granular capability of controlling your network as well as implementing security on top of that. Okay, just to wrap up, I will hand over to Tilina, just to.
Yeah, thanks, Manjiva. So some final takeaways and thoughts for you guys, right? Number one is you need good microservices to containerize, right? So I think that's probably stating the obvious at this point, but having a good microservice strategy will enable scalability, reliability, and good containerization. Once you have a good containerization and a microservice strategy, massive scale is really achievable through ECS, right? So a big kudos to the ECS team for making this available out of the box, right? So the auto scaling policies that Manjiva mentioned, as well as the task placement strategies really helped us go achieve this 20,000 TPS within 100 milliseconds for each call, right? And we've tried to break this as well. It didn't break, so it was awesome to see. Moving to containers, if you haven't done it, do it. That will simplify your life so much, right? If all the way from development to go to production, right? That's been awesome, right? And then ECS out-of-the-box capabilities such as ALB integration from day one, right, to ECS really helped us, right? Again, cutting down your development time and maybe also simplifying things and reducing complexity, right? So these were some of the big learnings for us. Big kudos to our development teams and partners as well. The main development team was based out of Hungary, right? So big kudos for them. And hope you guys enjoyed our learnings and the talk in general. We'll be around for another 15 minutes or so. Thank you very much.